Hello, I'm Alex Glaser. I'm a data science contractor from London, UK, and my talk is using Algorithm X to reanalyze the last UK general election. I don't know if anybody here has actually heard of Algorithm X or used it before. I will come to what exactly it is a bit later on, but I'm going to start off with talking a little bit about why I've ended up using it as well. And for that, I'm going to have to talk for a few minutes about UK politics as well. Hopefully, it will just be quite a quick overview. I won't go into too much detail. So basically, the main legislative body of the UK is the House of Commons, and it's got 650 MPs or members of Parliament. And the way that these 650 MPs are chosen is that the UK is divided into 650 what are called constituencies. They try and make them as equal population size as possible. Geographically, some of them could be a bit bigger or smaller, but try and have the same population in each one. And at every general election, each elector gets one vote. So they can get to vote for a party or a person who represents a political party. And at the end of the night, they count, and whoever has the most votes gets to win the seat. The seat is another name for the sort of constituency. So you get the most votes, you end up representing this constituency in Parliament. And this is what's called the first past the post method as well. And if the party wins more than 325 seats, they get to form the government, really. If they don't, then there's always coalitions or some sort of deal is brokered. Now, so basically, the UK doesn't vote directly for the Prime Minister. They tend to vote for a political party, and whoever leads that party then ends up becoming Prime Minister as well. Now, as with most voting systems, there's some pros and cons to it. The advantage is that it's very simple to understand. If you get more votes than anybody else, you get to become the member of Parliament for that constituency. And the other thing as well is that's also quite important for the people in the UK is that there's a link to your MP and their constituency. So, for example, if I wanted to let my opinion be known, I can write directly to my Member of Parliament. Now, I may not always agree with her, as I've got a female MP, but I may at least let my opinion be known. And that's a person who I write to directly if I want my opinion to be heard. Now, with regards to the sort of disadvantages of it, one may be that the majority may disapprove of the winner. So there's often a case, sometimes you can have somebody who has a sizable minority, but if, say, the opposition is split, then they still get in. And quite often you end up with, and often there are times as well where you can find people who win, but with very small majorities. You could have just two more votes than somebody else, and you become the member of Parliament. There's always people always say, "What's the most marginal seat?" And there have been quite a few seats in many over the years where people have only won by a handful of votes, really. And the other thing as well, whilst from a constituency point of view, this may seem quite fair, you get the most votes. Overall, the votes over the whole country are not really proportional. I'm going to sort of explain why this happened. I'll explain this in a table here from the last election. So Conservatives and Labour are the two major parties in the UK. And in the general election in December last year, we can see that the percentage here of votes that both parties got and the percentage of seats that they won. So, for example, Labour got 32.6% of the votes, and they got about 31% of the seats, which sounds sort of quite fair. Whereas Conservatives got 43.6% of the votes, yet ended up with something like 56% of the seats, which gives them a majority of 8 in the House of Commons, which is quite a large majority to have. This isn't like the most extreme example of a sort of a disproportionate result overall for the country. Probably one of the most notorious was in 2005, where, again, Conservatives, you can see here, got 32.4%, very similar to the result that Labour got last year. And they ended up with 196 seats. So again, quite proportional. Whereas the Conservatives, with only sort of a couple of percentage more, 35.2%, ended up with 355 seats, 55%. So, and it's, as I said, it's because there's this has, first past votes has a disproportionate effect. Now, because of this, after every general election, there's always calls for why doesn't the UK use a more proportional voting system? And in fact, most of the political parties, apart from these two, are in favour of this as well. And after the last general election, there was an article appeared online which basically said that if the UK had a PR system, these would be the results. Now, this was a day after, so the percentages you see here are slightly different to on the previous page because the results were still coming in. And they basically said that if they had, if the House of Commons would look like this, if based on the results. All they did was they took the percentage of results overall as a whole country, and they multiplied that percentage by 650, which is the number of seats in the House of Commons. And I remember reading this and thinking to myself, this is a bit too simplistic a model. Whilst PR systems do try and make a more proportional, try and make the amount of votes more number of seats in Parliament more proportional to the amount of votes that were given, it doesn't do it exactly as well. And I couldn't find another country that has a system as simplistic as this one. And the other thing as well is that, as I mentioned earlier, there is no link there between the MP and the constituency, which in the UK is considered to be quite an important factor. So I thought to myself, is there a way that, and also being quite pedantic as well, I thought I can see if there's something a bit more complicated than this. And I thought, is there a way that I could use the results from the last UK general election, use a PR method to try and see what those results would have looked like as well. Now, for those people who live in country, excuse me a second. Now, proportional representation or PR methods, they allocate multiple MPs to each political region. So as I mentioned, in the UK, we have one MP gets allocated to constituency, whereas PR allocates multiple MPs. So, for example, in Holland, the political region is the entire country, and MPs get allocated there. In Sweden, it's a geographical region, and in Ireland, they do have a constituency, but the constituencies have between 3 to 5 MPs who represent them in Parliament. So I thought I need to get a few ideas, a few rules. And one of the things was I wanted to keep the number of MPs the same. It could have been quite simple initially, just have gone, in each constituency, we can just treble or quadruple the number of MPs and apply a PR technique. Didn't want to do that. And then the other one is I only want to use results from the 2019 general election, i.e. no inference or prediction. Now, quite a few PR techniques, such as here, the single transferable vote, allow you to have multiple votes. So in single transferable vote, you're allowed to rank the people you want to vote for. Like you can put 1, 2, 3, 4, 5 there. Or you have other methods that they're having like Germany and New Zealand, where you get a constituency vote and a regional vote as well. Again, I didn't want to do that because that would have ended up meaning doing a lot of prediction, building another model, and that could have ended up being a lot more extra effort, really. So I basically tried to follow the Irish technique of having multiple MPs for a constituency, but what I would do is I would aggregate the votes with my merged constituencies. Now, that left the problem, how would you merge neighbouring constituencies as well? So to give you an idea of what the constituency map looks like, I've got here the constituency map of London. The UK is divided up into 12 what I call statistical regions as well. I thought I'd just look at it on a region by region basis, because I had a feeling that if I tried to use the UK as a whole with 650 constituencies, the combinatorics aspect of that would be huge. So again, this is a map of London after 2019. So the constituencies in red were won by the Labour Party. The ones in blue were won by the Conservatives. The one in gold were won by one of the other parties, the Liberal Democrats, as well. So I tried to find ways how could you actually merge neighbouring constituencies together. And I sort of tried a number of techniques. It was during lockdown, and I went through the rabbit hole of pentomino tiling, that's a sort of big area. It was, it interests me for a little while, but then I found out that it didn't quite work in this aspect. And then I was speaking to a friend of mine who suggested that if you are going to merge constituencies together, then they would actually only appear once. So if we merge two constituencies together, you wouldn't merge one of those with another one as well. And he said it sounded like an exact cover problem. Now, an algorithm X is something that you use to solve exact cover problems. So when you've got something where you want something to appear once and only once. So we've got an example here. We've got a universe U, which are the numbers 1 to 7. And we've got a collection of sets A to F here. And A to F represents sort of a random set of numbers. So here A is 147, B is 14. Now, is it possible to pick a subset of all these sets so that the numbers 1 to 7 are selected once and only once? So, for example, if I selected set A, I would not be able to include B, C, E or F in that because they contain one of those numbers as well. Now, the solution here is B, D, or F, and we actually solve these using algorithm X as well. Another way of looking at the previous problem was to maybe write it as a binary constraint matrix as well. So you can have ones and zeros in there, ones where represent the columns that are allocated, that are sort of part of that set, as well. And you can perhaps think of this, another way to look at this problem is say, can we select a set of rows so that the sum of each column is equal to 1 as well? And if you can actually represent your problem as a binary constraint matrix or something similar to that, then you can actually use algorithm X and exact cover. Probably one of the most famous examples is a Sudoku puzzle as well, where the numbers 1 to 9 can only appear once and only once in each row, in each column, and in each 3x3 grid. And the way the constraint matrix here is actually far too big to fit on any sort of slide. The way you'd build it is you would say that the numbers 1 to 9, you'd have each row would represent each possible cell, and the fact that the numbers 1 to 9 could appear in each cell. So you'd actually have 81 times 9 rows, because like you'd say that the first cell you'd have numbers 1 to 9, and then second cell numbers 1 to 9. So you'd have one of those for each. That would be number of rows. There are 4 constraints here. As I mentioned, the number can only appear once in each row. So it can each once in each cell. Once and only. So I'll start that again. You can only have one number in each cell. The numbers 1 to 9 can appear once and only once in each row. They can appear once and only once in each column, and once and only once in each 3x3 sort of mini grid in there. So you can create a constraint matrix of ones and zeros that say that if it appears here, it should not appear in these other areas as well. Now, I'm not going to give you an example here, but if you go to my GitHub code at the end when I show you some of the work I've done here, I do have an example with Sudoku puzzles as well, and I go into more detail about the grid as well. But it is actually quite fast when you run it. Now, there's lots of other problems you can solve using this. I think N Queens is probably one of the other more famous ones as well. And there's quite a few sort of websites that show you explanations how to do about when you can use exact cover. The thing about the problem is actually it's NP complete. There's no sort of fancy mathematics behind it. There's no sort of quick way of doing this. However, rather than actually using brute force, it actually uses doubly linked lists. And there's a thing called the dancing links method as well. And with that, it efficiently removes and inserts values in that. And this is what gives it its lightning speed as well. So you end up with a speedy backtracking algorithm. The actual algorithm X is basically it's recursive, depth first, a backtracking algorithm as well, and it does run incredibly fast as well. So much faster than using standard brute force. I'll tell you how fast it goes. So once I knew that this was how it worked, I then decided to say, okay, I've got a potential solution here. Given that we've got to merge neighbor constituencies together, I know they're going to appear once and only once. Can I then use algorithm X to merge them together? And the first thing I did was I used the disjoint command in GeoPandas as well to see if constituencies were neighbours. So I had shapefiles for all 650 constituencies in the UK, and I created data frames such as this one. So you can say set 1 is this place, and the other, and set 2 is this place, that place, and somewhere. So these, say for example, they would form a 3-way constituency link as well. Now, I limited myself to only merging 2, 3, or 4 constituencies together. The reason for this is that whilst in the UK, at the moment, you only get 1 MP per constituency, in the past, you were actually allowed to have multiple members. You were allowed to have multiple MPs per constituency. It was only in 1948 that it actually became law that you could only have 1 MP per constituency. Beforehand, you could have had multiple MPs. The most were actually 4. The most MPs they've had represented a single constituency was 4, where the City of London, where PyData London used to hold their meetups when we were allowed to, they used to send 4 MPs to Parliament for much of the 18th and 19th century as well. And in fact, up until, I said, like the first half of the 20th century, there were lots of places which sent 2, 3, or 4 MPs for their constituencies. So I limited myself to just 2, 3, or 4 in this case. Now, just to give you a rough idea of the sort of numbers we were dealing with here, this is for London, there are 73 constituencies. Now, if I wanted to merge 2 neighbouring constituencies together, I would have to obviously remove 3 of them, and so I'd have to have an even number there. The way I did this, I removed like a 3-way neighbour. I removed one at random, and then I was left with 70 constituencies. And I ran Algorithm X to say how many ways were there of combining 2 neighbouring constituencies. And the fact that it gave me roughly 540 million solutions, and that takes roughly 3.5 hours. So, yeah, that's quite a few. It's basically doing over 2 million solutions a minute, really. Now, I didn't actually need all 540 million of those, and I didn't really want to take 3.5 hours because I was then hoping to rerun this for multiple regions and for multiple number of seats being merged together as well. Now, there are a couple of ways to speed things up. The one thing about Algorithm X, it's actually non-deterministic. So if I were to put in another data frame, but the same data frame but in a different order, it would still give me the 540 million solutions, but it would give them to me in a different order. So one of the ways to actually speed things up was just to sort of run it for a few minutes, get a couple million solutions, take a random sample of those solutions, and then exit, and then shuffle the data frame, put it back in again, a couple of more million solutions, take a random sample. That sped things up as well. And the other way I found was to use a PyPy kernel. The Algorithm X code, which was written by a competitive Python programmer from Iceland, and you can just do a sort of standard pip install of this one. It was written in pure Python. It used sort of lists, and I found that if you use a PyPy kernel, you got a speed increase of up to 5-fold. Really, I know there are other ways of getting faster. Making Python code run faster, things like number in JIT and boost. This was the easiest way to make it work. I just got it running in a Docker container, and the same code ran as well. So given that I now have a quick way of sort of merging UK constituencies together, I ran it. I ran this for all the regions of the UK, and I was merging 2, 3, or 4 constituencies together. I also used it on JobLib as well because it was easily parallelizable. So the whole process took about 15 hours to run, and I ended up with several 100,000 ways of merging UK constituencies together. Now I've got that, I can then aggregate the results we had from the 2019 general election. So now that was all done, I now had to find what was a PR technique I was going to use for that. Now, if you're only allowed 1 vote, you kind of PR techniques methods can be divided into sort of 2 groupings. There's highest average or divisor methods, or remainder methods as well. So for the highest average methods, so after each round, the highest vote count gets allocated a seat. And then you divide the highest vote count by some number. And then again, you repeat the process. So whoever's got the highest vote count after you divide the highest vote after each round. And you repeat this until all seats are allocated. And then the second method is remainder methods, where you divide votes by a quota, and then you allocate this integer value to seats, and then any remaining seats allocated on the highest fractional remainder. I'll run through a few examples now because I think that might be a bit easier to understand. So let's imagine we have the scenario where we have an electorate of 200,000 votes and we have 4 seats to allocate. And we have Party A has 70,000 votes, Party B 50,000, Party C and D 46 and 34,000 respectively. The divisor here is the d'Hondt method. This is used in a number of countries, and it used to be used in the UK when they took part in EU elections. And we can see here after round 1, we just take all this, the divisor method is we divide the number of votes after each round by the number of seats plus 1. So in round 1, none of the parties have any seats. So we keep, we just do a full rank and just say, full count and say, who has the most votes? We can see Party A has the most votes with 70,000, so we allocate them 1 seat. So now for round 2, all parties B, C, and D's vote count remains the same, but Party A get their votes divided by seats plus 1, which is 2. So we end up now with 35,000 votes. And now Party B here has got the most votes because they've got 50,000 vote count as well. And again, so the next round we divide Parties B's vote count by 2, and we repeat this until all 4 seats have been allocated. So we see Party C wins a seat in round 3, and now in round 4, Party A has the highest vote count as well. So here, 2 seats get allocated to Party A, 1 gets allocated to Party B and C, and none to Party D in this method. There are more methods than just the single d'Hondt method. We've got the Webster method, which is also known as the Saint-Lagu method. And here we divide after each round votes by twice the number of seats plus 1. There's also the Imperiali and the Huntington methods, which don't quite divide the highest vote count as aggressively as either the d'Hondt or Webster methods. And these are methods that are used around the world. So that's a highest average or divisor method. With remainder methods, we're going to go with an example here as well. We're going to be using something called the Hare quota. We've got exactly the same scenario with 200,000 votes and 4 seats, and parties A to D had the same number of votes allocated to each one. And we see here the Hare quota is total number of votes divided by seats. That's 50,000. So we divide the total votes by each party by 50,000. And we can see here that we get 1.4 for Party A, 1 for Party B, and a number less than 1 for Party C and D. So if you take the integer value of that, we end up with 1 seat gets allocated to Party A because they had its value of 1.4, and 1 to Party B because, again, it's 1 or higher as well. And we're left with a remainder, so we just take the non-integer part of that. We can see 2 seats have already been allocated, and we're left with 2 seats. So we take the 2 highest remainder values and allocate a seat in that one, in this case, which are C and D. So we can see here that each party would win 1 seat in this format as well. There's another quota called the Droop quota as well, which is where you take, it's 1 plus total number of votes plus 1 plus seats as well, which in this case would be 40,001, which actually would give us the same results as well. So I now have multiple ways that I can merge neighbouring constituencies together in the UK, and I do have 6 different voting methods as well. So I now had lots of ways to simulate the last UK general election using Algorithm X and using a PR method where there is at least a link to the constituency and their MP. Now, I could have showed you lots of numbers, but what I wanted to do was find a sort of metric so that I could actually sort of compare the results together. And one of the ways of looking at it was to use the Gallagher index, which measures relative disproportionality as well. So this looks like very much like a root mean square error calculation. It's basically half the square root of half the sum of the observed percentage of minus the expected percentage. The observed percentage are the percentage of seats won in a parliament, and the expected percentage is the actual percentage they won in parliament. Now, generally, they say that anything over 10 gives us a disproportionate result. And for the last UK general election, those results were 11.6. So if I have a result less than 11.6, then I have sort of a more proportional result. So I ran it for 6 different methods. I merged 2, 3, and 4 seats together, and I ran 10,000 different simulations of the UK general election and calculated the Gallagher index and the mean and the standard deviation for each of these different scenarios. And these are the results here. I'm a bit old-fashioned in I like my means followed by the standard deviations in brackets as well. We can see that the standard deviations are actually quite small in comparison to results, so that gives us a bit more confidence of these results. Couple of things that I noticed, that we've got the Imperiali and the Huntington method, particularly when you merge 2 seats together, gave us more disproportionate results than we have at present in the first past the post method as well. And the other thing to notice is that the more seats you merge together, the more proportional results get according to the Gallagher index as well, which probably makes a bit of sense. So particularly the more seats you have available, the more you can spread the results against different parties as well. But we can see here that there were 2 methods that give us much lower results. And we can see the Webster method and the Hare quota method as well gives 4.3, Gallagher index of 4.3 and 3.2 respectively. So they're much lower than we'd actually get beforehand. Just by way of comparison, according to Wikipedia, the metric for Ireland is 3.2. And Sweden has and they, as I mentioned earlier, they use a single transferable vote. And Sweden has one of 0.63. They use a modified Webster method. And also they have much larger constituency sizes as well. So that probably might explain why that one's so much lower. But we can see here that the Hare quota method gave us a value of 3.2, very similar to the metric. It's very similar to the value in Ireland. So given that we've got the Hare method does give us fairly proportional results, I thought I would actually then compare these results with the simple model that I read in the paper many months ago with the actual election results. And just to remind you, they basically just took the percentage of votes and multiplied them by the number of seats in Parliament. And we can see here that the Conservatives, rather than 287 seats, would actually have won 295 using the Hare method. The Labour Party, which won 211, which would run 211 seats using the simple method, have 230. The Liberal Democrats and the Scottish National Party are the next 2 biggest parties. Liberal Democrats actually suffer slightly from using the Hare method. They get 11 fewer votes than a kind of a very basic simple model. And the SNP, Scottish National Party, end up with a similar number of seats as they would have done using the Hare method as a simple method. Whereas you can see in actuality, these results are very different. So to sum up, I basically saw a table in the paper several months ago and got quite annoyed and thought, is there a way that I could actually produce something which does using a data science method, data science techniques? And I think I've done that. And it was a little project that I ran during lockdown and sort of occupied my time whilst I wasn't allowed out, really. Just the final thing, I do want to say a few thanks and quick references. If you can see my slides, these links are available, but my GitHub code is on there as well that I used. There's also a Wikipedia article on Algorithm X and the dancing links method as well, which sort of sped things up about how you can then delete and insert elements of the list, which really sped things up. One of the reasons I sort of got into this was there's a guy called Joel Lindop in December 2019 gave a talk at London R about first past the post and PR, and this sort of got me started down this sort of rabbit hole and started thinking about these ideas as well. His paper is available there. I'm not going to attempt to pronounce the next guy's name, but he's the competitive Python programmer from Iceland who wrote Algorithm X Python code as well. There's also a guy who did wrote a PyPy kernel in sort of Docker container with a PyPy kernel, which used to speed things up. Lots of people from the community who have listened to me give this talk and helped me out as well. In particular, I want to say thanks to Adrian Dale, who gave me the idea for Exact Cover. And a final plug as well. I'm involved with a couple of meetups in London, or when we could actually go out. One I help organise is the data science workshop. There's lots of great meetups in London where you can go to talks as well, PyData being one of them. We're a bit different. We actually sort of work on code on problems. So we turn up there deciding we want to work on either Kaggle competition or a blog post or a new library as well. So we have many events at weekends and evenings. So again, hopefully, fingers crossed, we may be able to start those again soon. And the final one is Project Euler as well. If you don't know Project Euler, it's a website with 600 mathematical problems. Again, we meet up, we pick 3 of them to work on at random as well, and we meet up in a local pub in central London. There, again, obviously aren't happening, but we've got, hopefully, sometime next year, we'll be able to start those up again. Okay, I'd like to thank you for your time. I hope you found it interesting and learned a number of things about Algorithm X and UK politics and that kind of area. If you have any questions, I'd be happy to answer them. But thank you for your time. Cheers.